James Murray's undergraduate studies were at the Temple University and Miami University of Ohio. She received her PhD in physical chemistry from the University of New Orleans in 1986. After managing an analytical laboratory for about a year, she returned to this university to work with Peter Pulitzer in the areas of theoretical and computational chemistry. Her research specialties include the development and use of molecular surface electrostatic potentials and average local ionization energies to predict and interpret molecular interactive behavior. Since 2005, a large focus of her research has been in the area of non-covalent interactions, halogen bonding, and other sigma hole and pi interactions. Jane, the screen is yours.
Thank you very much. I first want to thank Professors Wozniak and Dominiak for inviting me to be a lecturer in this very fine series. I received an email on September the 29th of this year, and I thought about it for 2 days, wrote back and said yes, because I had an idea of what I could talk about. I became an electrostatic potential warrior when I joined the group of Professor Pulitzer in 1984. And I will say that one of our main goals was to fit in what we could at that time compute with things of interest to experimentalists, and that would be including crystallographers. And so before I move to my next slide, I just want to say there are many programs out there. Mine that I use, red is always the most positive, blue is the most negative. So if you're used to other color schemes, just remember red. Just remember elementary physics, okay? That's what we like to say. Okay. I would like to start with, again, I'm really talking about 50 years of the use of the electrostatic potential in chemistry and related fields. It was Aolo Scrocco and Jacopo Tomasi who introduced the use of the electrostatic potential in the early 1970s. And this was when you could compute the electrostatic potential with Gaussian 70. Many of you have never even, perhaps don't even know there was a Gaussian 70. But anyway, then about 10 years later, Peter Pulitzer and Ken Diker, who was a postdoc with Peter, published a chapter that was in the force concept in chemistry. And their goal, and I believe they had achieved this, was to cite every paper that included the words electrostatic potential. And today, first of all, it might be impossible because things change daily, and it would not be particularly useful. Okay, I will show my equation for the electrostatic potential at any point R. This is a Coulombic potential. If our electrons were point charges, this would be really easy to calculate, but we need a density. And therefore, the first term is very easy to calculate. You can do that with a calculator if you know where the nuclei are. Za is the charge on nucleus A, located at Ra, and rho of R is the electronic density function. And in regions where the nuclei dominate, you will have a positive potential. In regions where the electronic effects dominate, it will be negative. It's a physical observable, can be determined experimentally as well as computationally. It's a local property, and I say here that it has a value at every point in space, but that is not absolutely correct because it's not defined at the positions of the nuclei because you can't divide by 0. But anyway, that comes into play in some of the early work done with the electrostatic potential. It can be interpreted as the interaction energy at a positive point charge with the charge distribution at point R. And therefore, historically, the units for the electrostatic potential are those of energy, such as Hartrees, kilocalories per mole, kilojoules per mole. Are you able to hear me? Yes? Okay. Now, how can one present calculations of V of R? And I'm kind of giving the first three here on this, the three on this page, from when they were being used. In the 1970s, the prop keyword could be used to calculate electrostatic potentials at nuclei, to search for global minima. And you could basically read in any points you wanted and get both V of R and electric fields at points. And then at the same time, you could define a two-dimensional grid also using the prop keyword and plot that as a two-dimensional contour plot. Let me say that I jumped into this area using the prop keyword all the time because first of all, we were using Hartree-Fock wave functions. The electrostatic potential is a one electron property and therefore can be calculated even fairly nicely with Hartree-Fock wave functions. Then, starting in about the 1990s, early 1990s, researchers found that it was useful to plot the potential on some three-dimensional surface. That could be a van der Waals surface. We preferred using the electronic density as contours as a surface upon which to plot the electrostatic potential, typically using an outer contour, such as the 0.001 AU and 0.002. And so that was a big change. And then during this period in the 1990s, our group was also developing statistical quantities that were defined in terms of every point on the surface. They became very useful. I don't have time to talk about these so much now, but okay. And then here's 4, and this is something more new than what I just talked about. You can also compute V of R on molecular surface defined by larger contours closer to the nuclei of the electronic density, with the purpose of probing both inter and intramolecular interactions. And some of this work will be highlighted in this lecture. Let me see what time we have here. Okay. An example of one, and this plot also shows how we're going from 0, that's the nucleus, to about 5 angstroms on the horizontal axis. And you see how we spike as we're getting close to the nucleus. That's why it was never useful to plot the electrostatic potential in the plane, in a two-dimensional contour plot of a plane of a planar molecule, because it would be dominated by the effects of the nuclei. Anyway, this plot is one that I wanted to revisit some of the work where you can look at radial distributions. And these are for anions. The red is selenium -2 and the blue is arsenic -3. And I will say that back in 1989, Politzer and Sen showed that for a monatomic anion, you must go through a minima before you approach zero as you go to infinity. And these minima were found to be fairly good. And I mention this because it could be of interest, anionic radii. But my little arrows in this plot, the red and is for the selenium -2. That's where the 001 AU contour is. So my point is, if I plot these, I just get a red ball and a blue ball, like on my title page. But there's a lot of activity going on in here. And to this day, it can still be useful to use the prop keyword for a variety of things, of applications. Okay, here, and I want to, this is an example of the two-dimensional contour plots. And at the top left is 2,3,7,8 dibenzopyridioxin. I mean, tetrachloro. I forgot the tetrachloro, but there's 4 chlorines. That's TCDD. I apologize for that error. But at this time in 1985, I was given this molecule, but it was before I could do an optimization using Gaussian 80 for this. So what did I do? I went to the library and found the book with the crystal structure of TCDD and wrote, of all things, a Z matrix and looked at the potential. And what we see is that the aromatic regions, above the aromatic ring on 1.75 angstroms above the plane here in this first top left contour plot, no pi region, no negative region. The dashed lines are negative, but the chlorines are negative. And then what we noticed is that if you take the chlorines off, you have the oxygens have large negative regions, but not for TCDD. And we felt that this had something to do with the receptor interaction. But anyway, the TCDD was too big for me to optimize. We ran these calculations at STO5G. And so now an early example of plotting potentials on molecular surfaces. I show this one because it was an early example of this. We have carbon tetrachloride and carbon tetrabromide here. And red is the most positive, and there are positive regions on the extensions of the C, Cl, and CBr bonds. And this was unexpected. In fact, initially it was like, is there something wrong here? And then Peter Politzer gave a talk and showed this, and someone said, this can explain halogen bonding. This was in the 90s. It was at a solvent meeting. These are solvents. Anyway, okay. And I'm really going to do this quickly, but at the MIB2 conference in 2005, Peter had been keeping up with the literature as we did, and was following work by Alfinger et al. In the University of Strasbourg and Professor Rosnati in Milano. And he gave a talk really talking about their experimental work and showing some of our plots. And but just saying, we see positive regions. But Tim Clark was there, and as we left the lecture hall, he said, it's the sigma hole, and that we don't need this nomenclature, but it shows directionality, which is useful because the sigma hole positive potential, if there, will be along the extension of a bond, which shows anisotropy, atomic anisotropy. And these regions can be observed crystallographically and have been. And now it's gone to all of the first, columns 14 through 17, and even to transition metals. And I'm just showing here the top left is IH, and note that both the hydrogen and the iodine have positive regions, but the iodine has a lateral negative region, very typical. And this is SCl2, 2 positive regions, PCN3, 3. And here we have a silicon compound that has 4 positive regions. Some of them you can see. Okay, I'm showing very quickly some just electrostatic potentials on the 001 isodensity surfaces of, the top one is parafluorophenol, then paranitrophenol, and then anthracene. And what you see is that my key point here, if there's no significant intramolecular interaction, then you can say, oh, there's the OH, hydrogen, same thing here, the nitro oxygens. You can spot each hydrogen has a little positive region. In this case, yellow is also, yellow and red are often positive, and then green and blue negative. So these are just 2 more. This is, here we have orthobromophenol at the left and orthonitrophenol at the right. And I can see that I don't see the full halogen. I don't see my nice little hemispherical spot for the hydrogen in these. I can see that there are intramolecular interactions, but how, and I can imagine that the one on the right is stronger, but how much stronger? So just what I said, it's less easy to identify by looking at the potential at the 001 because the interaction is already happening and it's hidden within the surface envelope. Okay, great. Now I am moving on to this, one of my favorite molecules. This is chlorotrinnitromethane. It's got a really neat structure. And I didn't come up with this molecule, but our friends in Munich did. Michael Goebel was a graduate student of Professor Kloplutka, and he came running to us at a meeting in the Czech Republic in 2008, and he said, I didn't try to make this compound, but I did. And it has the shortest, and to this day, the shortest sp3 carbon chlorine bond in the Cambridge database. And so we went back. Of course, I had some travel laptop and I ran a calculation, and we could see right away that some very interesting things about this molecule. And one of them, and here in the abstract, it said this we use the computed electrostatic potential on the molecular surface to explain this contracted bond length. And let's see what I have here. Okay, there in this molecule, this is at the 001 AU on an 001 AU surface. And I can see, because by this time I've looked at lots and lots of potentials, and I can see that there's a little overlap. But the other interesting thing, the chlorine is entirely positive. A yellow here is positive and red is positive. And there are 3 upper nitro oxygens, and it's like they're attracted to that positive region. And it took a while to get this paper published because one of the referees was adamant chlorine cannot be positive. And then we said, well, let's look at bromine, bromo, trinitromethane, and fluoro. And then we wrote back and we said, but they're all positive. And finally, the editor agreed we would never convince this reviewer, and these molecules do exist with very contracted CX bonds. Okay, so to me, and there were other intramolecular interactions that I was interested in, but it seemed to me that the driving forces, for me to observe them, I would need to go closer to the nuclei. And it also seemed to me that the stronger the interaction, the closer I would have to go into the nuclei to separate the interacting parts. And so then I started experimenting with this in 2015, more of changing contours. And Peter, in his characteristic, thoughtful manner, suggested that I look at some intermolecular interactions as a test. So I did. And okay, at the very top here, I have an experiment. Okay, first I have molecule A and molecule B. I look at the potentials of them separately, and I can say, oh, we're going to get an interaction between the blue and the red. And you do. This is in equilibrium. And you don't see the driving forces. I know that. And many people know that. But you could find what was the contour for them to be nearly touching. And that happens to be the 0.014 AU contour. So we looked at about 20 complexes with ranging in strength from -2 to -13 kilocalories per mole. And we found the nearly touching points. It was very interesting that the volumes of these interacting parts leveled off at about 75% of the 001 of the 001 contour. So Peter was saying this is like how you can get an impenetrable volume, which would be about 25% of the 001 AU contour. Anyway, we had another paper discussing this also. And then just to be very clear, for those 20 or 19 intermolecular interactions, the nearly touching contours correspond to Bader's 3-1 bond critical points, but you have a different way of visualizing them. And I can verify that the presence of the bond critical points with the program I use. But it allows me to have a 3D visualization of what's happening. And generally, the value of the nearly touching contour is larger as the strength of the interaction increases. Okay. So fast forward to the autumn of 2022. I got an email from Hürtler Roos from the University of Lille in northern France, asking me if I'd like to revisit something I was doing upon her suggestion in 2015 on diethyl disulfides. And I said yes, and I still had a folder, so we ended up, and I'm just going to show this very briefly. She had a series of diethyl disulfides with different conformations, and some of them were relative energy of 0. And then there would be these ones that look like a staple. Look at the bottom plot here. Looks like a staple and has a high conformational energy. And what we found is that the higher the conformational energy, the higher the contour to get to this nearly touching point, as you see at the bottom here. And there, it happens to be between one hydrogen on a methyl and another one on a methyl, a 1,8, and there is a bond critical point. But we can see this is a repulsive interaction. This is causing it to be less stable. So then we continued with another kind of project. We looking at some other repulsive intramolecular interactions. If you look at the top left, you see planar biphenyl, and every hydrogen has its nice little red like hemisphere around it. But once you flatten out the biphenyl to make planar biphenyl, each hydrogen isn't standing alone. And the same thing for phenanthrene. And there are 3-1 bond critical points in both the planar biphenyl and the phenanthrene. And there was some people who were saying, oh, this is HH bonding, but it's clearly repulsive. And we can see the driving forces, the hydrogens are positive, and one of our conclusions that the existence of a 3-1 bond critical point is not sufficient for there to be an attractive interaction. It can be also repulsive, as with the diethyl disulfides. Now I'm switching to a recent paper entitled Quantifying Water Hydrogen Bonding from the Surface Electrostatic Potential at Varying Isodensity Contours. My collaborators are listed. They are in Belgium or working in France. And first thing, and this goes back to statistical properties, quantities we developed in the 90s. So water is an extremely electrostatically balanced molecule. Then I will talk about some small molecule interactions, alpha lactose interactions, where we're using actually experimental data for the lactose, and then some protein-protein interfaces also where we're getting big structures from other from the protein data bank, etc. Okay. Right here, and the molecule on the far left is water, and the middle one is hydrogen cyanide, and the third is ammonia. And one thing I want to point out, look at the very narrow bands of nearly neutral potential between the blue and the red for water. These are much bigger or wider in the other molecules. And the very interesting thing, at least I think, is the positive and negative surface areas at the 001 AU contour are identical, and the most positive and most negative potentials on this surface at the left of water are equal in magnitude. And this is not the case for the others. In hydrogen cyanide, the hydrogen is more positive in magnitude than the negative region, and in ammonia, it's the reverse. And another thing about water is if you go to higher contours of the electronic density, water holds its negative potential. And here we have 0.0175. I'm looking at the plane. I'm looking into the plane of HOH. And then here's another view. And this is 0.038, but I'm able to keep that negative potential, and this is not the case. You saw what happened with the disulfide, diethyl disulfide stable and other molecules. As you go closer in, you lose the negative potential. Okay, so here we looked at some just small molecule interactions with water. Water, methane, water, HCN, water, NCH, water ammonia, and then water methanol, and some others where there were double interactions. And you basically see that as the strength of the interaction increases, so does your, I mean, these are negative, but as we go this way, let me see. Yeah, here we go. We go here to a higher contour for the, you know what, I'm having trouble because I'm standing up and I can't see the numbers on this. But anyway, yes. The top one is the ammonia with the hydrogen of water, because the ammonia's negative region is more negative, and we're up here about more than -6, and we're at a higher contour of the electronic density. Okay. So then we looked at here I'm showing two views of the electrostatic potential of alpha lactose. The one on the left is the 001. I call it a big blob. And then the 033 AU. It's very interesting here. You can see the intramolecular interaction here. And that's why this is basically a good contour for this molecule. It's ready. It's got these OHs that can flip around. And that's what happens when you hydrate lactose. And I know that my time is running out, but I want to point out here that we have water in 5 different spots, and all of the interaction energies are calculated to be around between -10 and -11 kilocalories per mole, roughly -5 per hydrogen bond. And this one actually is the strongest, and one can analyze this in more detail, and we have done that. We have also looked at lactose crystals, but I'm leaving that for you to read if you're interested in this paper. Okay. Then we looked at protein-protein interfaces, and what we did is the protein interfaces came from the protein data bank, ID 3U43. And what we did is we made models and focused on particular waters. And the nice thing about the visualization, you can see is it interacting in 4 sites, which water can do, 2 through the negative and 2 through the 2 positives. And so we have water here, we have water here, and accordingly, we find that the stabilizing protein-water interactions in which water is water is simultaneously a donor and an acceptor of hydrogen bonds, and it can be up to 4. And what I've been talking about in this section was intermolecular interactions. I'm going to just show this slide. This is an example of a halonium ion interaction where what we're doing is looking at HCN, and this is NCH, neutral, the potentials far apart. And then I'm looking at the Br plus cation in the middle. It's totally positive because it's a cation, which is the case. But it's like it has a pee hole. And many researchers, Professor Erdele and Professors Rissanen in Scandinavia have made some amazing things with these bromonium ions. And when you do a calculation on HCN, Br plus NCH, you get a big blob, but then look how close to the, I have to go to the 0.101 AU contour of the electron density to separate the interacting species, and calculated delta E is about over minus 150 kilocalories per mole. Really strong networks. I just thought this, but that follows. These are very strong cation. Yeah, there's a mistake there. Okay, that should be NCH at the top. Okay. Now I'm concluding comments. Both electron densities and potentials are physical observables. Isodensity envelopes give shapes, while the electrostatic potential is the first step in understanding a molecule's interactive behavior. Changing the contour of the electron density upon which to plot V of R can be useful and has been useful in both inter and intramolecular interactions. We look for the nearly touching contours and find that they follow the strengths of the interactions, particularly for interactions of similar types. And 3-1 bond critical points are usually found for 1, 5, 1, 6, 1, 7, 1, 8 intramolecular interactions, but are not always present, but they're not always associated with attractive interactions. And finally, interactions with water, a particularly balanced and unique molecule, are dictated by the available partners in interaction. There is much more to explore. I want to thank you for your attention. I want to acknowledge my talk is dedicated to Peter Politzer. And note the quote by Richard Feynman in the bottom right, if you can see it. It says, you can recognize truth by its beauty and simplicity. The quote at the top, I like that. This was on Peter's bulletin board in his office. It's a quote by R.J. Robert Oppenheimer talking about how life can be hard, but we have to go through it. And help others and be kind. Anyway, I just love the fact he typed on an old-fashioned typewriter. This probably, look, it's yellow, this piece of paper. And there's a picture of us at a Mardi Gras parade in New Orleans. And I want to acknowledge many of my collaborators. It takes a village, and here are some of the members: Ralph Blasi, Tora Brink, Felipe Bulat, Tim Clark, Mark Lensick, Kevin Riley, Hudla Rose, and Danny Von Poke. Thank you for your attention.
Thank you, Jane, for this excellent lecture, and which is now open for comments and for questions. And before they appear, maybe I will ask the first question. I remember a long series of papers of yours and Peter focused on different correlations with different physical properties. Could you comment a little bit more about applications of electrostatic potential and this kind of studies?
Yes, again, I've been talking about 50 years of the electrostatic potential, but I could talk for 35 minutes on this topic. What we discovered is, well, what we didn't sit down and say, oh, we're going to do this, this, and this. We organically came up with statistical quantities that we felt were useful. So you have an 001 AU surface and the potential. So then you count how many positive points, how many negative points, the values of these. We came up with a local polarity where it was the average deviation of the electrostatic potential on the surface. That's independent of whether it was positive or negative. And these would follow like Camlet and Taft's polarizability polarity parameters. We're talking about way back when. And so this was interesting. Then we came up with another statistical value. It's called the variance, but we got the positive variance and the negative variance. And then we use these variances to come up with a balance parameter. And that is where water stands out. First of all, it's very small, has high local polarity, huge variances of the positive and negative, and they're the same. So if you multiply the balance parameter, which water has the highest possible value, which happens to be 0.25, if you multiply that by the variances, then you can get like how interactive is a molecule with itself. Because, and that's, we had, correlations with boiling point, critical constants, diffusion constants, you name it, log P. It was pretty, and then typically you would need for some of these a volume, a size value. So you could use surface area or volume. We got all of this coming out of the program that I use, and it's used. I still find it, and again, very useful to use these properties because they mean something. When the variability, when the variance is high, it means you have a from the neutral point to the most negative, you have more change. And anyway, that's in a nutshell an answer to your question.
Thank you. Florian, could you ask your question yourself?
Yes, I wasn't sure whether I was allowed to speak again. Thinking about the current developments that we see in electron diffraction, and for example, Paulina also having had a go at using electron diffraction data and electrostatic potential models to refine them. What's your personal take? Is the experimental error of electron diffraction in a regime that is trustworthy enough to do these very, very delicate, because you do so sophisticated and very, very deep understanding analysis of the electrostatic potential? Can we directly use the experimental electrostatic potential, or do we have to be careful there because it is a delicate matter? So what's your opinion on this?
Well, let me ask you this. We always Phil Coppens and and Ed Stevens was finding electrostatic potentials in Cheryl Klein experimentally. And so but I believe in the time when this was happening, they did the two-dimensional contour plots, slicing through the crystal. And how do you show yours?
Since in electron diffraction experiments you have three-dimensional information and you can refine against three-dimensional diffraction data, you have the full three-dimensional but possibly limited resolution Fourier series of the electrostatic potential available. So basically the question is, how susceptible is the electrostatic potential in such a Fourier series, like a Fourier reconstruction of the electrostatic potential in periodic boundary conditions, towards, let's say, experimental errors and these kinds of things?
You know what? I wish I could answer your question properly, but may I say that I will make a comment about basis sets and methods. Okay. Some time ago, it was about 10 years ago, one of our colleagues, Kevin Riley, who we've done some work with in halogen bonding in the past, he was writing papers and always got the people complaining, why are you using 631 GDP? Okay. And so Peter, Kevin, and I, and some students of his, we did this kind of very extensive paper where we showed lots of density functionals and Hartree-Fock, and with different basis sets. And we basically said, you just need minimally a split valence basis set with polarization functions. You don't need to go to you're wasting, even if you have a lot of computing power. Yeah, I can run augmented CC, PVTC potentials, but I don't always need to, And by the way, I must say, even in these days, I'm finding some very useful things to do with the prop equals read keyword. It's prop equals something or prop. If you just say prop, you get a list of all the atoms in your system and the electrostatic potentials at the nuclei, which are fairly invariant to environment. I mean, carbon in any molecule, even anion, cation, will be around -14 something. I mean, I know them in my head.
Well, that's very, very interesting, because it can directly be related to experimental data. Then, good to know. Thank you very much.
The Hellman-Feynman theorem can be used to formulate static equilibrium conditions for the electron density, not necessarily ground state. This could be used to put crystallographic refinements on a self-consistency scheme. Do you know of anyone having tried this?
The answer is, I believe in the power of the Hellman-Feynman theorem, but and it's, forces, anyway. I do not know that someone has tried this.
Okay.
Yeah.
Dusan Malenov, thank you for the wonderful lecture. ESP is usually plotted on 0.001 atomic unit density surface, but sigma holes on chlorine atoms in some cases cannot be seen that way. Do you think that if we plot them on a surface with the larger electron density, they could be seen? Would that be considered a valid sigma hole? Many greetings, Serbia.
You're asking me, may I say something about chlorine, okay? If you look at methyl chloride, it's basically going to be almost neutral at the end with a negative region. And so, but if you put fluorines on or electron withdrawing groups and look at chlorotrinitromethane, the entire chlorine is positive. I mean, entirely, because in that plot, red and yellow were positive. But basically what we have said is, even for chlorine, you can see a little anisotropy. Let me backtrack to good old Richard Bader. And I mean that. I cite Richard Bader in every article that I submit. But he published data of molecular chlorine. And you can just see the anisotropy. And then you can see that the positive region would go to the lateral side of another one, of another chlorine. And this is Cl2. But what we've always said is that even if you do not see a positive region on a chlorine, if you look at the distance from the chlorine to the surface and then perpendicular, you will find a difference because there's more electron density around the lateral sides. And so we say, even there has been in the past a lot of question initially, but now it's fluorine can be a halogen bond donor. It's just that it's so small and you have to have a lot of electron withdrawing groups. But if there's a bromine or an iodine out there, it's not going to be able to do its thing because it's so small. But that we showed some of this, and we said fluorine still has anisotropy and the entire surface may be negative, but we can create molecules that exist where it's positive. And well, when Peter first presented this to a group of people interested in halogen bonding in Milano, it was like, no, fluorine can't hydrogen bond. It's the same old thing. And then Professor Rosnati became a big advocate. We did a couple of papers together and then once you convince someone who is totally on the opposite side of something, they become, very big advocates of that. And so anyway, I would say that if you put any halogen, or if you look at chalcogens and you look at the distance from the nucleus to the positive region or along the extension of the bond, you will find that distance is shorter than perpendicular where you might be hitting a lone pair. And so we feel that it's kind of like you can engineer the strengths. They're very tunable, all of these regions. And I like to sometimes say, we can talk all about this without the use of the word sigma hole, and then there's the pi hole. We used to just say there's a positive region, there's a negative region, kind of say where it was, but there is the usefulness, particularly of those that nomenclature, is it imparts directionality. And so we'll let it be. We didn't plan this. Tim Clark said, it's the sigma hole. And then everybody now writes papers and doesn't even cite, no citations, but anyway, yeah.
Thank you. I'm very much convinced that with the development of the quality of electron diffraction data, Paulina has done first quantitative studies of electron density and electrostatic potential. So there is a big future and for both theoretical and experimental developments in understanding of the role and applications of electrostatic potential. So especially this, I love this backing from experiment these days from electron diffraction. That's Paulina. Can you comment also a little bit on this?
Yeah, so at the moment it seems that the errors are huge, but also the effect of moving slight amount of charge is much better visible on the electrostatic potential than on the electron density. Mm-hmm. So somehow it compensates. So even if the data quality nowadays are not of the level we are used to with X-ray diffraction, for me it's amazing that you still can extract some useful information from this noisy data, even if you not use the proper dynamical scattering approach. It's because the effect is really huge. It's like moving around tiny amount of electron change electrostatic potential a lot. And the Fourier approach may actually help you because it focuses only on larger distances, so the valence regions. So the Fourier maps are not dominated by potential generated by nuclei, which is really dominating when you compute it directly from the quantum mechanics.
I would be very interested in some of what you're doing with this, and Professor Wozniak. I think it's very exciting, and I do feel that, yeah, I think the only way to handle this would be to be able to compute the electrostatic potential, or you can find it experimentally and compare. Yeah.
Yeah. Yes, Julian Hen is thanking for your nice lecture and for answering his questions. The last chance to ask question to Jane. If not, then let us thank both the speakers for excellent lectures and for these vivid discussions.